And good morning, everyone. Welcome back to Math 154 as always. Week 7, lecture 2, not lecture 2. You know what it is. We're going to go over a few due dates, some you've seen, some you haven't, and then we'll pick up where we left off. So 3.1, due on the 12th, 3.2, due on the 14th, 3.3, due on the 19th. The only new one there should be 3.3. In fact, that should be the only new due date on the screen at all, because we will finish that today. And then, let's see, Excel 2.4, we talked about that previously. CPI is going to also be due on the 12th, same day as 3.1. That pay attention quiz and Canvas, we talked about some very specific details about that one last time. So if you did not watch the intro to last lecture, make sure you go back and do so, because there's a decent amount of paying attention you have to do in this in terms of what you read and what to look for, as well as how you answer the question, and that I'm going to be pretty strict on, hey, if you say not a complete answer in terms of what I'm looking for as a QR student, then I don't have to give you any partial credit necessarily. Maybe I will, maybe I won't. It's a pretty common issue with this quiz, so pay attention. No sentences for the answers, no paragraphs for the answer. It's just a number, or a number in a word, or a number in abbreviation, something like that. All right, so with that being said, shouldn't be too much of a long intro already. We're going to pick up where we left off in 3.3, and then we'll get into 3.4. We will not finish 3.4 today, since there is no due date on the screen. That is hopefully obvious. And just a warning that in the next week or so, we are going to start talking about the project that we'll have to do. So that'll be on the horizon very, very soon, but let's pick up 3.3 for now.
We had done the Bulkin on a budget problem, and I had some more writing up here, but I don't save the file with the writing. So if you need to see those notes, the writing parts, you can see it in last class. But I mean, it's basically right here. Ultimately, I just don't have the written parts of how we figured out where the 384 and the 120 came from. But what we were working on at the end of last class was not this page. That'll be today. Was this page. And we said we still had to do, I think it was 3 through 6. Yes, 3 through 6. Okay. Yeah, we'll just do it here, and we'll deal with the silly annotate. But I want to get my calculator out first. Over this side, there we go. Okay, so the rate of prescriptions per 100 adults. So we already did 1 through 2. We're starting on 3. The rate of prescriptions per 100 adults, which I guess it would be nice if you could actually see, dang, what that number was. So yeah, I'm just going to have to leave this zoomed out, unfortunately. That's okay. So we're starting on number 3. The rate of prescriptions per 100 adults. So we have the 14, I can't see. I've got this cursor over it. There we go. In 2011, nearly 14 million monthly prescriptions were written for American adults aged 20 through 39 for ADHD, and there were 82,364,000 adults in that age range, which we also determined were 82,364,000. All right, I'm going to rehide that and then just use my little piece of paper. Okay, so the rate of prescriptions, which was the 14 million, so the rate of prescriptions was the 14 million, are X's per, why am I writing it above? The rate of prescriptions, that is not just the 14 million. The rate means there's 2 things. So it's comparing prescriptions to people. So it's 14 million prescriptions per 82,364,000, and I'm just going to write that number with all the zeros and everything. So this is ultimately trying to reduce this to a per 100. So per 100, if you just do this division off the cuff, what you get is 1, 4, 1, 2, 3, 4, 5, 6, divided by the 82, 364, 0, 0, 0. There we go. And we get 0.17 blah, 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 blah. So I think we rounded that to 3 decimals, which ended up coming out to 0.17. Yes, we did. So that was 0.17, and that would be prescriptions per, and I forgot to write adults. And yes, it's in that specific age range of 20 to 39, but I don't want to have to write all that detail. So 0.17 prescriptions per adult in the age range. But they wanted this to be seen as a per 100. So per 100, a simple way to do that would just be to multiply by 100. And what you would get is 17 per 100. So 17 prescriptions per 100 adults, which is like having 17%. So this would be us scaling a quantity to 100. And you might say, well, how did I know just to do this as a times? Well, I could have set it up as a proportion. So the alternate looking version of this, where you have your 0.17, and that's per 1. So you're going to scale your rate. So the rate is in the top, and then your people in the bottom. And we're going to scale it to 100 instead. So then you have, well, what's the rate per 100? And then you're just cross multiplying, and you can see you're going to take the 0.17 times 100. So again, either way does the job, as long as you don't end up dividing by 100, because then you would have 0.0017 per 100, and that wouldn't make sense. If it's 0.17 per person, if you've got 100 people, that number is going to grow. That's the idea there. So the same thing just keeps going on. So per 1,000, you just take the 14 million prescriptions and divide it by the 82 blah, 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 which ends up being that, that same number, but then you're going to multiply it by 1,000 instead. The same idea, you can set up your proportion and take a long time and get the answer, and you end up with 170 prescriptions per 1,000 adults. If you want to scale this to 100,000 people, well, you take that same division, the 14 million, and you divide it by the 82 million. And that was prescriptions and then adults. And yes, I just rounded the number, but I wouldn't actually use that. Sorry, that get a little sloppy. As I've said before, there's no algorithm making my handwriting better in this, so it looks awful. Even my handwriting is not this bad on a whiteboard. This looks terrible. And then you're going to multiply it, sorry, not equals. Do times 100,000. And some people would have this answer as 17,000. And then it would be prescriptions per 100,000 adults. But the thing is, when you scale to 1 decimal place, when you actually have this division, if you show it, let me come off of annotate, 14 million divided by the 82364, 0, 0, 0, and then times the 100,000. There we go. The answer here, because you're multiplying by such a large number, all the decimals that were at the end of that 0.1699 blah, blah, blah number originally now are significant. So it's 16,997.7. Oops, what happened there? So a more accurate answer is 16,997.7, and that would be prescriptions per 100,000 adults. So number 1, that answer was the 0.17. That was RXs per adult. Number 3, 4, and 5 are all the same concept. We're talking about prescriptions per some number of adults. It's just the first one is scaled to 1 adult. The third one is scaled to 100. The fourth one is scaled to 1,000. The fifth one is scaled to 100,000. Why would any of us do this? Which one's the best answer? That's what number 6 is, and I've mentioned before that this is subjective, which means it's opinion. So one person might think that the first one is the best because it's the simplest, it's less than 1. Maybe they just like decimal values and they like thinking about per adult. Another person might say, well, I like the answer to number 3 more because the answer, since we scaled it to 100, we've talked about how scaling to 100 relates to a percent. So a lot of people like to think of things as percentages. So 17% of adults in this age range are expected to have an ADHD medication. Number 4, people that deal with statistics in media generally would like that one because a lot of the times they'll scale to 1,000 adults, and that's because of this. Whenever you have a really, really, really big number, you get these commas clustering every 3 zeros just for our eyes' sake, for our sanity's sake. But if you do per 1,000, it's basically like you just eliminate having to write 3 zeros. That's the idea of doing something per 1,000. So per 100 is good for percentages. Per 1,000 is just good for taking bigger numbers and getting rid of 3 places. The fifth one, why would we scale to 100,000? Well, when we actually do the division and the multiplication and don't round until the very end, you get what feels like a more precise value. It didn't get rounded nearly as hard as that 0.169 just going up to 0.17 or 17 or 170. It feels like a more accurate value, a more precise value. So some people will like that one and they'll say, okay, well, I'm just going to scale to 100,000 people. I would say I least prefer the last one unless you're going to be dealing with large numbers. If you're going to say, all right, I've got the state of Virginia, which has what, 7 or 10 million people, roughly 14 million, somewhere in that ballpark. How many people in Virginia do you think have an ADHD medication? If this statistic was true for all adults, not just that particular age range. So if I was going to be dealing with a large number like the population of the state of Virginia, then I would actually like that last one for the accuracy. But if I'm going to go into a classroom of, say, 20 people, and I wouldn't actually ask this, but if I were going to and say, well, what percentage of people do you think in this room have a prescription? So it's not asking who actually has it. I'm saying, what do you think? Well, based on the fact that 17% of people have it, I would just take 17% of the 24 people in class and boom, I'd have my answer. It would be much easier that way. It would be easier to do with the small one. And you could even just use the 0.17. You could take 0.17 times the class population because that's literally the same thing as 17%. 17% is the same as 0.17. It's just anything as a percentage is scaled as 100 people, so it looks bigger. And that's something we're going to study extensively in chapter 4 is percentages as numbers and rates and things like that. All right. So sorry for me kind of stumbling at the beginning, getting the numbers in straight. Like I said, I have some menus up here for Zoom as a teacher that you can't see, and it covers up this entire portion of the screen. So if I cover it, I can't see it. All right, clear. Let's go off of annotate, minimize, scroll down. And I don't want to write on that again. So let's just make a new document. This, do that, sidebar it, boom, there we go. I'm not going to do all of these. I'm just going to do the first 3 or 4. For each question, determine the answer with proper units. The first one has been done for you. And I actually want to go through and do that work anyways. So it says $5,100 divided by $300 per month. I kind of don't like the way they put the dollar symbol after the 300 here, but it's not wrong. It just looks wacky. Usually when people want to put money annotations after, they would go USD instead, unless we were talking about cents, because the cent symbol goes at the end for some reason. So we're doing some multiplications and divisions with units, and we've very vary. There's no need to say vary. We've seen many examples of multiplying, especially with the dimensional analysis, that whole out with the old, in with the new. This isn't really out with the old, in with the new necessarily. It could be. This is just saying do the problem, but pay attention to the units. Sometimes they might cancel, sometimes they might stack. Just see what happens. So for number one, again, like I said, we're going to do it anyways. We take the $5,100, and then it says divided by $300 per month. Now, some people might write it this way, and then $300 per month. Remember, the word per always means a division and the thing goes in the bottom. And you might say, well, Mr. Beckner, you already had a bottom. Well, I did, but the thing is, that $300 per month is its own entity. So when I divide by that, it's going to have an extra fraction. And this gives you that compound fraction idea that we've lightly discussed. But the idea is that these two things will be the same. It's $5,100, and then I like to do the division symbol, and then $300 per month. I think this is better because how do we divide fractions? We multiply by the reciprocal, which means flip. That got ugly. We only flip the one after the division symbol, not the first one. So this becomes $5,100, and then I'm going to use red for showing the change, times, and now the month goes in the top, and the $300 goes in the bottom. See, what's critical here is that it's not just the number going to the bottom, it's also the units swapping places, and now it looks like I got a Madden drawing. It is not just the number that switches places, it is also the units, which is why it's extremely important to know that the dollars went in the top and the months went in the bottom. Why did I know the months went in the bottom? Because the word per came before it. Easy as pie, easy as per. All right, so let's see what we get. Well, the 5,100 is going to divide the 300 because they're top and bottom of each other. So we'll do 5,100 divided by 300. And that turns out to be 17. Okay, so 17 is our value. But then what about the units? Let's see if things cancel or if they stack, because they could stack. The dollar, the other dollar could be in the top, and then you've got dollars squared, which would make no sense. Okay, but it doesn't in that case. Dollar in the top, dollar in the bottom, they're gone. The months are in the top, they didn't cancel, so that's why the months goes in the top. So I'm not going to say this is an alternate to number one. Let's just say this is a different problem. Let's say instead of this being a division, what if it was a multiplication? What if it was $5,100 times $300 per month? What would this problem give us as an answer? Would it make any sense? Could it actually be relative to something in this world? Okay, well, the 5,100 times the 300, that's just math. 5,100 times 300, which would give us a big number, 1.53 million. The dollars are not top and bottom, they're both in the top, so they stack, so it's dollars squared. The month is in the bottom. What in the heck is this? This makes no sense. What is a dollar squared per month? In terms of a rational real world thing, it doesn't seem tangible, which means there's probably no reason to be multiplying these two numbers. What is the point of me doing this alternate problem? Again, not an alternate version of the same problem, an alternate problem. It's using the same values, multiplying instead of dividing. The point is that math on the back of a napkin thing I've talked about. There's a whole field of mathematics that basically just say, if you're trying to play with a couple of numbers that have units and rates and all sorts of things, and you're trying to make sense of it, to analyze something deeper, whatever, if you can multiply or divide these things with their units and they cancel ultimately to give you something that makes sense, if something just in meters or something that's just in dollars or something that's just in months or dollars per month, something that is a tangible concept, then that means you probably did it right. Again, an entire field of mathematics says you probably did something right as long as the units in the answer make sense. you open up a whole world of mathematics, like talking about how a lot of people know that an ant is 10 or 100 times stronger than its weight. So if an ant weighed a gram, it could lift, let's say, 100 grams. But that's a teeny tiny ant. If you scale that ant to the size of a person, by doing some of this math where you're just multiplying and dividing things and doing some volume to surface area comparisons as well, because it has to do with muscles, it turns out that if you had an ant the size of a human being, it could still only lift 100 grams. It turns out that if you had an ant the size of the Empire State Building, it could still only lift 100 grams. And again, people have showed this argument by just multiplying and dividing things and getting units that make sense. It's not like they have to go develop a random formula for it. Again, literally books written on this. Just try multiplying and dividing things. If you get an answer with units that make sense, then it's a logical answer. At worst, it's off by a factor of 2 to 3. That's about it, the worst thing that can happen. All right, rant aside. Number 2, the one that hasn't been done yet. 400,000 people times 6.2 meters squared per person. So a meter square is a type of area. So this meter squared per person is a population density. It's talking about how much room each person gets. And then it's saying, all right, well, this is how much room each person gets. What if we have 400,000 people? How much room do we need in total? So we have these two figures that someone gives you, and then you go, let's pretend like I didn't actually tell you to multiply this. Maybe you're doing the first thing times the second thing. Maybe you're doing the first thing divided by the second thing. Maybe you're doing the second thing divided by the first thing. I don't need to see say the second thing times the first thing, because that's the same as the first times second. Order of multiplication doesn't matter. So I'm just saying I give you a problem with these two values, and I ask you, well, how much space do they need? This math on the back of the napkin concept just says multiply or divide these numbers until you get an answer that makes sense in terms of units, and boom, there's your answer. So maybe you think you're supposed to divide these things, and if you did that, you would get an answer that wouldn't make sense. So I'm going to do this different problem first, but I'm going to come off of annotate. Clear the screen, off of annotate. So again, different problem. Let's just say again, I gave you a word problem that said you have 400,000 people, and this city or state or whatever on average has 6.2 meters squared per person. And I say, how much space do you need for all these people? Something like that. So all I give you is those two numbers, and you think maybe I'm just going to divide them. So I take 400,000 people, and then I divide by 6.2 meters squared per, so bottom, person. Now, people and persons are the same thing. People is not persons squared. It's just like having an S at the end of person. Persons, people. So you might say, oh, these cancel. Nope, they don't, because this is a division. We don't start doing math with division. We have to change this to 400,000 people, then times persons, aka people, over the 6.2 meters squared. And when you do this, the 6.2 is in the bottom, so we're going to divide. So we take the 400,000, we divide it by 6.2, and that number is, let's just round to the nearest tenth, 64,516.1. 64,516.1. The people and the person, let's just say that's people, so that's people squared. And then on top of meters squared. What in the heck is a people squared per meter squared? That doesn't make no sense. So I could certainly just give you that as a problem and ask you, hey, pay attention to the units, give me these squirrely units in the answer. But again, the point is, you would have these two numbers in the real world in a word problem, something like that, and I don't tell you to multiply or divide them, you got to figure it out. So you go, all right, well, I tried multiplying them and this gave me nonsense. So, or, excuse me, I tried dividing them and it gave me nonsense. So maybe I'll instead do the actual problem and I'll do the multiplication. Let's try multiplying them. Now again, fair warning, it's possible you need to swap the order of the divisions and that would give you an answer that makes sense. But we're just going to go straight to brass tacks and say that this is what we're doing. The 6.2 meters squared per person, aka people, So now we have people top, people bottom, they cancel. We're going to take the 400,000 times the 6.2. And we get big number, 2.48 million. And that's just meters squared. So that is the answer. And this does make sense for several reasons. Again, the context problem here is you got 400,000 people, and these people are used to having or have on average 6.2 meters squared per person. So in other words, if I put one person in the middle of the field and I say we got to social distance them and they get 6.2 square meters, that means that the area around them, if you took the length times the width, it would equal 6.2 meters squared. So maybe that's like 2.3 meters by 2.3 meters, something like that. Let me get the exact answer. In fact, square root of 6.2. I was really close, 2.5. So basically you're in a box of a width about 2.5 by 2.5 meters. So again, the problem is, well, how much space do you need for all 400,000 people? First of all, that different problem I made up in us trying to BQ our students in the real world and just having two values and playing with them, it made no sense, A, because of the units. It also made no sense if one person needs, let's just say, about 10 of these meter squares, how do 400,000 people only need 64,000? Because each one person needs about 10, so 10 people would need about 100. That means 100,000 people would need about 1,000,000, which means 400,000 would need about 400 million, excuse me, 4 million. I said that wrong. I did another factor of 10. And again, that was me just rounding the 6.2 up to a 10. So that's some extreme rounding, which is why 4 million is close to this. It's still in the same order of magnitude, but there is a big difference between 2.4 million and 4 million. But either way, this answer in terms of size, magnitude is another word for size, makes much more sense than 64,000. Meters squared is a measure of area, so the units make sense. So that's 2 check marks for the answer making sense. So number 3. All right, we got 20 miles and 40 miles per hour. So again, this word problem that might relate to it is you're in a car going 40 miles per hour and you've got to cover 20 miles. How long is it going to take you? Maybe that's the problem. Maybe that's the problem. So again, you have a car and you're going 40 miles per hour on average, and you've got 20 miles to cover. How long will it take you to make that drive? In fact, I'm going to type that up for fun. So you're going 40 miles per hour and have to go 20 miles. How long will it take? So this is the real quantitative reasoning problem to number 3, and this is just the math that you end up doing. So maybe you try doing the 20 miles. So again, let's try this. Again, and I'm going to do this wrong. I'm not doing what problem 3 says. Let's say, oh, I think I'm going to multiply these. So you go 40 miles per hour, and you go times 20 miles. Well, 4 times 2 is 8, so you stack the zeros and you get 800. Miles times miles is miles squared. The hours is still in the bottom, and this makes no sense. Okay, so maybe it doesn't work with multiplication, so maybe you try dividing. So the next thing you try is the 40 miles per hour, and you go divided by 20 miles. Well, that's, excuse me, 40 miles per hour times, now the 20 miles was in the top, so it now goes in the bottom. There was nothing in the bottom originally, which means there's a 1 there, which means there's now a 1 in the top. Okay, well, the 40 divided by the 20 in this instance is a 2. The miles do cancel, but look at where the hours are. They're in the bottom, so it's 2 over hours, which means it's 2 per hour. Does that make sense? Is that a time? No, that's saying you're going 2 per hour. 2 what? 2 bobs? 2 oranges? It doesn't say, it's no units, it's just 2 per hour. So no, that actually does not make sense. So the answer is not 2 hours or 2 per hour. So then we do the actual problem, we say, okay, well, the only thing really left to do is 20 miles divided by 40 miles per hour. Okay, so that's 20 miles then times the hours now go on the top, the 40 miles go in the bottom, the 20 and the 40 reduce to a 1/2 or a 0.5 if you do the division. 20 divided by 40 again would be 0.5. The miles cancel, the hours are now in the top, and we have an answer that makes sense. The units are good, which means the number should be good. And it does make sense. If you're going 40 miles an hour, well, 20 miles is half of that, so you should be able to cover that distance in half of an hour, because you would go 40 miles in 1 hour, but you only need to go 20 miles, so it's definitely going to take you less than an hour. This makes sense on all levels. As I've said several times now, this is an unbelievably amazing field of mathematics. It's ridiculously basic, but it can open up so many doors. So this is a skill that I would love for you to all have, but you can't just play with the numbers. You can't just say, oh, we'll do 40 divided by 20 or do 20 divided by 40, because then you might think the answer is 2, which it actually isn't. You go, well, 2 seems like a reasonable amount of time. But again, when you actually play with the units, you prove that the 2 is not the answer, it is the half. And again, you could, if you think carefully, logic your way that the answer is not 2, because again, if you're going 40 miles an hour, that means in 2 hours you would cover 80 miles, because the first hour you'd cover 40 miles, and the second hour you'd cover 40 miles for a total of 80 miles. Amazing field of mathematics. Try it out, use it, love it. There is another field that is inside of this where you do what's known as a volume to surface area argument. That whole fun little ant strength problem is what that's based off of. You can talk about water boiling in a pot based on volume to surface area arguments, because your water takes up a volume of space in 3 dimensions, but your burner is only covering one of those dimensions, one of those surfaces. So the heat's applied only to the bottom surface. It's not applied to the top. It's not applied to the sides. Yes, the sides do heat up a little over time, but really the main source of the heat in a boiling water pot is the bottom of it. The sides just basically heat up to keep the ambient temperature inside. Heat sources at the bottom. So I had a fun little experiment in college where I took 2 pots of water and turned them on. Well, I did all the math first, and I made my argument of whether if you took 2 pots of water or just 1 pot with the entire amount of water from the 2 pots, which one would actually start boiling faster. And I won't say the answer because that would take all the fun out of it. But I did the math beforehand. I had an argument with an old person over which one was going to be right or wrong. And well, they weren't as keen to the math of surface area to volume arguments, so they were wrong. I didn't gloat. I might have gloated a little. It's what you do with your parents, right? When you're right, you gotta be like, hey, I'm right. Okay, so that, I believe, will close it out for the section. Yes. So let's close, well, I might not want to close that. Back to this. 3.4. Now, admittedly, 3.4, all the fun, we are not going to do the main idea of this section. I would really want probably 2 full weeks just to talk about dosages of medicine. And it doesn't have to be medicine, but just dosages in general. We usually just talk about it with medicine. This is still the same idea of math on the back of a napkin. It's very similar to dimensional analysis with the old and with the new idea. The idea with dosage problems, like you've got this much medicine and you need 2 cc's per pound, and you need to administer this much medicine to this heavy weighted person. I'm not saying they're heavy weighted, just like they're 150 pounds heavy, 170 pounds heavy, whatever. How much medicine does that person need if it's a very strict regimen of 2 cc's per pound or a 1/2 cc per pound or whatever it might be. And you can get into all these different conversions and multiplications and divisions, and there can be 5 or 6 or 7 of these products and cancellations. And it's a solid type of problem. It's a great concept. But the amount of manipulation you have to do, just like with those last problems I was doing where I was just taking 2 values and figuring out how to multiply and divide them, In these problems, you end up doing 5 or 6 or 7 of them, and it can be a true struggle of trying to get the setup correctly. You can really circle around the same problem and not get anywhere because you keep trying setups that fail, and you have to learn how to basically predict where to put the next piece of the puzzle. So again, it's solid, but I want to keep being able to do this stuff for weeks on end, and we don't have that time because then we wouldn't get to any of the stuff at the end of the course, which is where my true passion is. So we're going to focus more on the idea of concentrations, which admittedly will never come up again in this course, but it is an awesome type of problem. And then we're going to talk about densities. Densities, which would talk about like you've got this much weight of an object and this much volume to cover it. What's the density of it? So, you know, I don't want to jump the topic. So concentrations. Concentrations and rates are tied together. Concentrations are a type of rate. But before we actually get into the official discussion of this, let's have some fun. And this problem is a lot more fun when you're in-person class, in an in-person class, especially when I don't actually bring M&Ms to class. That's why I say in theory. So a teacher brings M&Ms to class in theory. So I just gave you all virtual M&Ms. I've got 50 of my virtual M&Ms in the bag, and I'm going to distribute them to 5 students before class. So let's say it's 3 minutes before class and 5 students are in the Zoom call. And I say, all right, for being early, I'm going to take my 50 M&Ms and I'm going to give them to you evenly. So it's not like one student's going to get 7, another student's going to get 12. It's if one student gets 8, the next student gets 8, the next student gets 8. I want to be fair. So what is the rate of pieces of candy to each student? So I'm very specifically asking you for a rate, and I'm telling you what I want that rate to be. If I don't tell you what I want the rate to be, you'd have to say, well, what would the most logical decision be? Would I want to go people to pieces or pieces to people? But I've told you specifically to go pieces to students. So we're going to go pieces to students. That will be our rate. Remember, rates are just fractions with different units. They are ratios. The word rate and the word ratio sound the same. They have the same root word, R-A-T, because they're the same thing. It's that easy. All right, so we got 50 pieces. I'm not setting up a proportion here, so I do want to write the units per 5 students. It's very easy to do that division. You're going to get 10, and that's 10 pieces over students, or 10 pieces per student. And I think that makes sense because student 1 gets 10 pieces, student 2, student 3, student 4, student 5 get 10 pieces. If you add 10 plus 10 plus 10 plus 10, you get 50. How much candy I had in the bag? But uh-oh, I forgot to I didn't distribute my digital M&Ms before class. I didn't do it on time. And all of a sudden, right at the start of class, 20 more students show up, which is a bit exaggerated for this because half of y'all aren't watching live, and that's okay as long as you're watching. But let's just pretend I had 20 more students show up. And so I'm not actually I'm gonna say, all right, well, the people that I was giving the candy to, give it back to me. I know, that stinks. You'll still get some, but you're probably gonna get less, right? If I gotta give candy to 20 more students, that means everybody's gotta get less because I only have 50 pieces of candy. So hopefully nobody ate any, hopefully nobody licked their fingers for various reasons, especially now. So now how many students, now how many does each student get? And we're going to stop right here for now. Let's worry about this last bit later. Let's not put too many questions in our head at once. So we got 20 more students, not 20 students total. So our ratio of pieces to students, why did I do double colons there? That was weird. All right, so now we have 20 more in addition to the 5 we originally had. So it's 25 students, excuse me. So it's 50 pieces to be distributed over 25 students. 50 divided by 25 being 2. So now it's 2 pieces per student. And you're like, why even bother? You're just going to give me like a taste of an M&M. At least it wasn't 100 students, because then you'd only be getting half. And I don't feel like cutting M&Ms in half today, especially the digital ones. Okay. So what's the point of this? What's the point of this having some M&Ms, having a small amount of students, giving them, taking them back, then having a large amount of students and redistributing them? This is the idea of a concentration. 10 pieces per student is the concentration of candy to students. This is a concentration with a different population. 2 pieces per student. So a concentration is a rate. I'm going to say it 2 more times. A concentration is a rate. A concentration is a rate. It's a rate of something that you have to distribute amongst a population, maybe a population of people, or maybe an object space. So maybe a volume of water or a surface area of something like that, or something like that. I meant to say not of. Okay, so now let's get to the second part of this. I'm underlining the wrong thing. If you multiply the number of students and the number of candies each student gets, what is the answer and is this consistent? So I'm asking you to do something very specific. I'm sure you're not surprised. I want you to multiply the number of students and the number of candies. So we'll have case A, which was the top one. So that we're going to multiply the number of students, which there were 5 students, and then times the number of candies each student gets. The number of candies each student gets is the rate, 10 per student. Making sure we're doing our math accurately, we're setting up our fractions accurately, units in correct places, anything after a per goes in the bottom. Students cancel, 5 times 10 is 50, and you get 50, and the units that are left are pieces. Okay, well, how about scenario B? In scenario B, we now had 25 students, and the rate of candies per student was 2 pieces per student. I don't just say 2 pieces because then your students wouldn't cancel and you'd think it's 50 student pieces, 50 pieces students. That sounds weird, doesn't it? It doesn't make sense. So you can't miss anything. Students cancel like this though and you get 50 pieces. And that was a weird spelling, it looks like. P-I-E-C-E-S. Is this consistent? 50 pieces under case A, 50 pieces under case B, it is consistent. What is the point of all of this candy nonsense? What's the point of this concentration stuff? Usually when we talk about concentrations of something, it's not as fun as candy and students. We're talking about a pollution over a volume of gas, or a water pollutant over a volume of water, or something like that. Or maybe a concentration of just any kind of chemical in a bed of water or some other thing. You can talk about the concentrations of lipids or fats in milk. You got your 2% milk, your whole milk, which is 4%, your 1%, your 0.5%, your 0%. So you can talk about the concentration of fat to the milk in that situation. So in the previous problem, we were using pieces of candy and students. It is literally the same concept as if you use any of these more complex sounding types of things. So the concentration, which is a rate of an amount per unit of volume. So above our quote volume was people above. So volume doesn't have to be a literal volume. It can just be the amount of the thing you've got to give the other thing to. So a concentration, which is a rate of an amount of candy per student, or an amount of fat per volume of, say, water or liquid. So if you take the concentration times the amount of volume, which was this thing right here, these two A and B scenarios, this was the concentration times the amount of the substance. I have it backwards, actually. The first thing is the volume. The 5 students was the volume. The 10 pieces per student was the concentration. And same thing here, the 25 times the 2, that was the volume times the concentration. So if, where did I go? If you only change, I'm sorry, the concentration times the amount of volume should give this the total substance in the liquid, which is exactly the same thing. This 50 was the total substance. This 50 was the total substance. because you have the same amount of things to distribute amongst either a smaller volume or a larger volume. So if in one scenario it's 2 pieces per student, the other scenario with less students, you're going to get more. So if I just say, all right, I've got 50 grams of fat, and in one case I've got 1 gallon, and in another case I've got 2 gallons, then that means there's going to be a higher concentration of fat in the thing when I toss it in the 1 gallon bucket versus the 2 gallon bucket, which is how you end up with your whole milk versus your 2% milk, essentially. I mean, they filter it versus just actually placing it in, but you get the idea. So this is the concentration formula. This right here is this right here. If you take one scenario's volume times its concentration, if you don't change any of the parameters, you just have more or less people, more or less fat, more or less liquid, whatever, that product has to be the exact same thing as the other scenario's volume times its concentration. So this particular product, the left and the right side would match, and what do they happen to equal? They equal the total amount of the substance, so the total amount of fats, or the total amount of poison, or the total amount of whatever it might be, the cleaning agent. You can talk about so many different concepts here. All right. What page was it? Page 137. How are we on time? 20 minutes. Not that, this. Page 137. So again, I will admit, in this course, this is not something that we are going to repeatedly see over and over and over. I'm very honest about what we'll see over and over and what we won't. We see ratios all the time. It never goes away the entire semester. We'll see the concept of proportions pretty much until we hit chapter 6. And then that idea is still just extended into a higher concept, kind of like inverse proportions is a higher concept. So while we won't really see this much again, it is still an important idea. And now for question 1, we're not going to do all of question 1. We are going to skip mainly A, B, and C. We're going to skip A, we're going to skip B, we're going to skip C. This is just an alternate way of kind of getting to the same point, but without any rhyme or reason. That's what I was trying to say. It's just us arbitrarily saying, well, let's do this and then do that and do this and then do that. So let's go straight to trying to apply the thing we were just talking about so we don't forget it. So this is the concentration equation, but with more appropriate letters for this problem. Why do we get to use it? Well, let's think about it. Your roommate walks at 3 miles per hour and it takes her 8 minutes to walk to class. You, however, have the same class but walk at a much faster pace at 5 miles per hour. 5 miles per hour is hardly a walk. That's a jog for most people. In fact, I would say for most people, that's a run. 4 miles per hour is about the speed, the rate of, distance versus time, not just time. 4 miles per hour is about the speed for most people, where it starts getting really challenging to, instead of just power walk, to actually start jogging. And the difference between power walking and jogging is jogging, you'll have both your feet in the air at some points, whereas power walking, you always have one foot on the ground, no matter when it is. And I've seen some fun little arguments over those two things before. It's kind of silly. Either way, not the point of the problem. So you walk slower at 3 miles an hour and it takes you 8 minutes to walk to class. But your roommate, who walks much faster at 5 miles per hour, maybe a really solid power walk or a mild jog, how long will it take to get to class? This is actually a concentration idea because you both have the same distance to cover. That's the same, quote, volume, if you will. So you have the same distance to cover, but one of you is going to cover it faster, which means that they should be able to do it in less time. If you increase your speed, it should take less time to get somewhere. This is not an idea of a proportion. Concentrations are not direct proportions. Again, concentrations are not direct proportions. They are not proportions. You can't use y equals kx for this stuff. You can't go fraction equals fraction in the traditional sense of proportions. Notice I said they're not direct proportions. They're actually inverse proportions, but let's not get into that at all. So we're going to take the 3, the 8, and the 5 and just plug them in here. I am going to use the annotate for just simplicity's sake. So there's two cases here, and that's what the little ones and little twos are for. So are for. So case one, case two. Case one is you. You are case one. So this 3 miles per hour, that's your rate one. This 8 minutes, that's your time one. All right, then the other person, oh, I'm sorry, case one was the roommate. Case two, that's you. You walk faster at 5 miles per hour, that's rate two. So you is case two, and I said that funny intentionally. So your goal is to find how long it will take for you to get to class, which we'll call T2. So we're just plugging those numbers into the concentration equation. Again, this is not a concept of proportionality. And you might try to use this as a proportion. You might say, oh, okay, well, 3 versus 5, that means the 8 minutes is going to go up by 5/3. And you would say that answer ends up being 13.3 minutes. If you're walking at 5 miles per hour, you're walking faster than your roommate. Let's just say you both started at the exact same time. You started walking. You're going to get ahead of your roommate instantly. Why would it take you 13.3 minutes to get to class if you're taking the exact same path and your roommate's walking slower? That would make no sense. So you go, well, wait a minute, this can't be a proportion. That makes no sense. Throw it in the trash can. Maybe it's this concentration idea because we have the same amount of thing to cover, the same amount of distance, our quote volume in this instance, but we're doing this at different speeds. So those different speeds are kind of like the different amount of students in that last case. All right, so R1 is 3, so we're going to plug in the 3 here. Now here's what's cool. The rate was in miles per hour, the time is in minutes. Those are not the same units. So you go, well, that stinks. I need to convert one of these things to miles per minute, or this to 8 hours. I'm sorry, or this to hours, which would be less than an hour. But the awesome thing about concentration equations is if one thing has this particular pair of units, so R1 has a particular pair of units, that means R2 will have the exact same pair of units. You don't have to actually manipulate them. If T1 has a different type of unit, then T2 would just match the same units as T1. So that's what this first problem was actually kind of doing. It's going what we would have done before we got to this section. It's saying, well, convert the minutes to hours because these aren't the same thing. Then you can figure out how far away class is based on using those two numbers, multiplying, dividing them, however they make sense. And then you can, figure out, all right, well, if that's the distance, how long is it going to take your classmate to do it if they're going to go at that speed? But instead, we're doing it this way. So not going to even put the units, just the 3. The T1 was the 8, so that's times 8 equals the R2. We know it's 5. Well, we don't know the T2. That's our unknown. Well, 3 times 8 is 24, so that's 24 equals 5T. That does not look like 5T. You're then going to divide both sides by 5. And then 24 divided by 5 is going to be 4.8. Yeah, 4.8. I don't want to have to pull the calculator up for that. So we get 4.8 is equal to T2. T2, the first time was in minutes, which says that this is 4.8 minutes. Again, yes, one of these things has hours, one of these things has minutes. In terms of actual dimensional analysis, it feels like it wouldn't work. It feels like you'd have to cancel everything, but the beauty of this concentration formula is that you don't have to. The time in one thing is the time in another thing. The rate in one thing is the rate in another thing. So it takes your roommate 4.8 minutes to walk to class, which is the exact same answer you would get if you do it by method 1. Yeah, so this is awesome. Does it make sense? Well, it took your roommate 8 minutes at a slower speed, so you're going faster because you're late, I guess, maybe, or you just naturally walk faster. And that's me. So 4.8 minutes, that's less than 8. So that's in the bounty of making sense. Now, again, yes, the units are just automatic, so you can't use them as a gauge of making sense, unfortunately, but this is still a great tool to have up your belt. And I'm going to need to clear my screen, so if you don't have the notes yet, remember, go to YouTube, pause it. All right, problem 2 and 3. Problem 2, you have a fixed budget for flooring your new home. One type of flooring costs $4 per square foot. I feel like this problem is dealing with my real life right now. And that $4 per square foot covers 89,280 square inches using your budget. Oh no, one of these things is in square feet, the other is in square inches. Thankfully, because this is going to be a concentration style problem, because we still have the same amount of space to cover, no matter what scenario we're under. So we don't have to worry about the unit conversions. We certainly could, but it's going to be extracurricular. All right, so $4 per square foot will cover 89,000 square inches, which again, you could convert to square feet, but we're not going to. But you go, well, I like the $4 per square foot, but this $6 per square foot, this fancier one, this more expensive one also looks really nice. And they say, well, how much flooring would you actually be able to cover on your budget? So on our budget, they didn't say how much money we have, but we know that we can cover this much volume of flooring, if you will. And again, that's a poor name for that, which is why I said it so exaggeratedly, because it's a true surface area, or just area, if you will, but we can call it a quote volume for the concept. All right, so if you buy more expensive floor, obviously you're going to be able to buy less flooring. So we're going to be able to buy less than about 90,000 square inches. But how much will we be able to cover? So maybe we got a house and we know that this house is, let's say, 50,000 square inches. So the first one, the more budget priced one, we can definitely cover the house if it's only 50,000 square inches. But what if we were to buy the more expensive one? So the $4 per square foot, that's the first rate. How do I know it's a rate? Because it has the word per, it's got two different types of units. Then A1, that's the area, that's A1 there. The more expensive flooring is $6 per square foot, that's the second rate. How much flooring will we cover? Well, that's A2. So we just jam those numbers in the formula. R1 was the $4, skipping the units here because it'll look really weird otherwise. The algebra will terrify you with all those units in place. We don't like to solve equations with units in them, and that's what this is. This is an equation. Before, we were just doing what we call expressions. It's not a left side equals a right side. We were just taking a number and multiplying or dividing things. All right, so 4 times the 89,280, and then equals to the R2 was the 6, and then times our A2. I am going to pull out the calculator this time. Otherwise, you might not trust my numbers. So we're going to go 4 times 89,280. So that's the left side. That is going to be 357,120 equals 6 times A2. We're then going to divide both sides by 6. So divide by 6, come off with annotate. And we get 59,520. That's our A2, but don't just say that's the answer. 59,520 is not the answer. What was the first area measured in? It was measured in square inches, so this is in square inches. So it's 59,520 square inches, or you can go 59,520 inches squared like that. So if you had a house that was 50,000 square inches, yes, you would have enough to be able to buy the pricier one. You would have less wiggle room because you're going to make errors. You're going to have to make cuts and stuff. So waste, usually say get to 10 or 20% more. So you're getting pretty close to, you know, if you make too many mistakes, maybe you'll have to go a few bucks over budget, because 60,000 would be 20% of that. 20% more than 50,000, that is to say. All right, finally, my favorite one, number 3. Just do that. Oh, nope, can't do that. Let's put it over here. Good enough. Janine eats 1/4 cup of oatmeal per day, also known as 0.25 cups per day, and a container lasts her 36 days. This is her by herself. So her husband starts eating 1/2 cup a day. How long will the container now last with both eating cereal each day? So, January and a little bit of change into February. Janine buys a box of cereal. She eats oatmeal. Oatmeal cereal, same thing, right? And she's eating 1/4 cup of oatmeal per day, not a lot, and it ends up lasting her 36 days. All right, so box 1 of oatmeal finishes. Janine or husband goes to the store, maybe together, maybe separate, doesn't matter. And he or she, buy more oatmeal. But the husband goes, you know, I'm going to get on this oatmeal train. So it's not just Janine eating oatmeal, it's Janine and the husband eating the oatmeal. And they say, how long will the container now last? So here is where people make their mistakes. They go, all right, this 1/4 of a cup per day, so that's the first rate. So that's our R1. And I'm going to go ahead and convert it to a decimal just to make things a little easier. It's 0.25 cups per day. The husband eats 1/2 cup per day. So that's another rate. That's the husband. That's R2 equals, and that would be 0.5, question mark, question mark, question mark. And I'm going to go ahead and say that no, that's wrong. That's wrong, and I'm going to show you why it's wrong. So let's, for red, pull out why this would be wrong. Oh, by the way, I forgot to mark what T1 was. That'll be correct. T1 is 36 days. We want to know what is T2, the time of the husband eating. Actually, no, that's not right. It's not just the husband eating, it's the husband and the wife eating, which is why what I'm about to do is wrong. So they'll say R1, that's the 0.25. T1 was the 36, so times 36 equals R2. We said is 0.5, but I'm telling you it's wrong. Just bear with me and we'll see why. All right, so 0.25 times 36 is going to be, what is that, 9? Yeah, that's 9. So that's 9, and then equals 0.5 T. Just divide both sides by 0.5. I'm not going to change colors. And 9 divided by half is the same as 9 times 2, but you got your calculator, so you don't need to know that. And you get 18 is equal to T2. But it makes no sense. Why does this make no sense? Because it took 36 days for Janine to eat this oatmeal by herself. If the husband was eating by himself, he's eating twice as much, so it should take half as long. If you're only eating 1/2 cup a day, it would take 18 days. But it's not just the husband, it's Janine eating 1/4 of a cup and the husband eating 1/2 cup, which means they're eating 3/4 of a cup or 0.75 cups a day, which means it will take less time than half of the original time. So a lot of people will say 18 days makes sense because it's less than 36 days, but when you think about it deeper, yeah, it's kind of ballpark, but because it's the two of them eating, it was the 0.5 that was wrong. That is not the consumption rate. So let's actually do this correct now. So correct, R2 is actually 0.75 per day. And that's what 1/4 plus 1/2 is. That's 0.25 plus the 0.5. This is the actual consumption together because they're both eating. It's not just the husband eating 1/2 cup, it's him eating 1/2 plus the wife eating 1/4. So the correct problem is 0.25 times 36 equals 0.75 times T2, which you still get 9 on the left, but now you'll be dividing by 0.75. Again, not going to change the color. 9 divided by 0.75. It's going to be 12. So that says that 12 is equal to T2. The time was in days, so it's 12 days, and that does make sense. All right, we only have a few minutes left, so I'm going to skip number 4 and go straight to number 5. Clear my screen. I'll give you another 10 seconds. And again, I know that this problem right here, a lot of people would think the 18 makes sense, but that's because this has an extra little convoluted piece to it, the fact that you have to add those, but they don't tell you that. You have to really think, all right, they're eating together, which means it's not just the husband eating in the second scenario, it's both of them eating, which is why I added those to get that 0.75. All right, now let's clear, scroll. Okay. 4 and 5 are pretty similar, but 4 is in scientific notation, so it would take me a little longer than the 6 minutes we have left to get into all that. So let's just go straight for 5. We were never going to do 6 because it requires systems of equations, which is not a math topic that we assume you've had in here, believe it or not. All right, so you have a solution mixed at a concentration of 5 grams per milliliter. Oh, good Lord, solution, volumes, mixtures of concentrations? This is terrible stuff. I don't understand this. All right, you have a class and you're giving them 5 M&Ms per student. That's the same thing here, 5 M&Ms per student. That's the rate. It's just a rate. Don't worry about the concept. And you need 100 gallons mixed at 4 grams per milliliter. Not only does this question not say, what thing are you finding, it asks you a true quantitative question. What do you do? Huh? What do you do? What are you talking about? Let's ignore the question for a second and let's just try and solve the problem. So we're a store and we're a chemical store, and our chemical, we have a volume of liquid and the concentration of the chemical in it is 5 grams per milliliter. So every milliliter of this liquid has 5 grams of this substance in it, maybe alcohol, maybe thieves cleaning solution, so thieves agent, whatever, I don't know, doesn't matter. Rubbing alcohol, whatever. So every milliliter has 5 grams of that cleaning solution. Well, unfortunately, a customer comes in, Bob. Bob says, "Sir, good day. I need 100 gallons, but your concentration is a little too strong for my needs. I need this to be a little weaker. I don't want 5 grams per milliliter. I only want 4 grams per milliliter." That's what the what do you do aspect, that's where the what do you do aspect comes into play. The fact that the concentration we have to offer is too strong for our customer. So that's the what do you do, but again, that'll be the last bit. For now, 5 grams per milliliter, since that's a rate, so that's rate 1. The 4 grams per milliliter would be rate 2. And then you have to be careful. Does the 100, is that going to be, and by R, they're using C, so let me just use the same letter, C1, C2. Rates are concentrations. I said that earlier. The letters are interchangeable. I could have written that as R1 times V1, R1 times V1. So the 100 gallons, is that the first scenario or the second scenario? Well, your store offers the 5 grams per milliliter, and the customer comes in and wants 100 gallons. So the 100 is with the customer. So this is V2 actually, not V1. We're trying to figure out what volume we need, to get for them. So the equation goes 5 for the C1, the V1 is the unknown, equals the C2, which would be the 4, times the second volume, which was the 100. Well, 4 times 100 is 400, so we get 5 times V1 equals 400. We will then divide both sides by 5. And then that's going to go in, what, 80 times? Yes. So the volume of liquid that we need to give the customer is 80 what? Well, the customer wants 100 gallons. That was the units of their volume. So our volume needs to be 80 gallons of our liquid. So that's what we need to give the customer. Hold on. The customer actually wants 100 gallons. At the concentration we have behind the counter, in order to get the total amount of the cleaning agent, the thing in there at 5 grams per milliliter, we only need to give the customer 80 gallons because it's stronger than what they need. So in order to get the total cleaning agent, they want 100 at a weaker solution, so we only give them 80. But the problem is the customer says, don't give me 80 gallons mixed at 5 grams per milliliter. I want 100 at 4 grams per milliliter. So what do? You need to dilute the liquid that you're giving them. You need to give them 80 gallons of what you have in stock, but since they want 100 gallons and it to be weaker, you just add water. How much water? Well, you got 80 gallons of the stronger stuff. If you need to give them 100 gallons of the weaker stuff, you add 20 gallons, and that is how you will achieve it, by putting 20 more gallons of just pure water, something that does not have that concentration. You will dilute the substance, you will get them the volume they want, and it will be at the appropriate strength since we use the concentration formula to get there. that is the same concept to problem 4. So problem 4, I'll give you the answer if you'd like to try it. You'll have to look up the scientific notation with negative exponents if you're a little rusty, but negative exponents just mean the decimal goes left. So for instance, and I only have like 30 seconds to talk about this. Oops, nope. Clear first. Clear. So they give you 10 to the minus 3, which means you move a decimal left 3 times. They give you 10 to the minus 4, which means you move a decimal left 4 times. When you end up solving this, if you want to try this on your own, you will find that V1 equals 10. But this is another scenario of they want 100 gallons of something, or excuse me, 100 liters of something, but then you only need 10 liters from behind your counter, so you add 90 of water. Add 90 liters of water to give them their 100 liters that they want. I'm sorry, not liters, milliliters. Milliliters. The concentration was measured in a per liter, but the volumes were measured in milliliters. So I will say this one more time. In terms of this course, this is not a topic that's going to pop up in chapter 4 or 5 or 6 or 8 or 9 or 10 if we actually get there. However, this is still a very cool concept that you can use in the real world. This is another case of if we were in person. I have a concept that I like to use in class that applies to, let's just say, everyone 21 years of age or older, but I won't actually say it out loud since, I don't know, like I said, I try and keep things G-rated. All right.
And on that note, we're going to go ahead and call it a day. So like we said, 3.1, 3.2, and 3.3 all due on the horizon. Your Excel 2.4 CPI due the same day as the 3.1 My Math Lab homework. You've also got your pay attention quiz. Make sure you've got that done by the 14th. Make sure you're answering that as a QR student like we explained last time, and very, very briefly this time as well, but much, much more detail about that quiz and what I mean by that in the previous lecture, week 7, lecture 1. All right, so per usual, if you have any questions, you can email me. Please stay up with this work. Please keep studying. Please keep working hard. Remember, you are still supposed to be reading ahead. So if you have, or when you have that opportunity, make sure you're always, reading ahead in the next section, not for an hour or 2 hours or anything like that. At least 15 minutes to put your eyes on the subject material, and you can at least look at the notes to share. Besides that, have a good day, and we'll see you next time.